Good morning, everyone. So yeah, I'm from IREC in Barcelona. I will present this advanced energy management for the systems that were presented before. So not to repeat again, but these two types of system were presented before. So they both, so the dual source and the solarized, both have different energy sources, different storage. Further than only the innovations of the heat exchanger and the performance itself of the systems, we also need advanced management and control to further improve the overall performance of these whole systems. That's why we have developed these smart controls that can act on the different parts, so whether the loads, the storage, the sources, receive information from them, and also interact and send control actions to them. This comes from identifying some challenges that heat pumps are not always used optimally, can result in high electricity bills. Also, the maintenance could be not always very often done, so they operate sometimes below their design efficiency. And they can create also peaks of electricity consumption if we have a very high rate of penetration of heat pumps. So for this, we have developed these two algorithms within the 3HP project. The first one is the optimal energy management. Its goal is to minimize the energy cost and also increase the share of renewables used in all the systems. And the other is the efficiency drift self-diagnosis system, which is aimed at facilitating the maintenance and increasing the reliability. So both algorithms are independent, but we consider them together as algorithm for the management and control of the heat pumps. So they are fed with different things such as the sensors and forecast of weather, occupancy, and prices. So getting a little more in details about the advanced energy management system, it's structured in two main modules. We have this central controller, which is the core of it. It includes an optimization problem on 24-hour horizon, fed with a different forecast and measurements. But this is updated every 15 minutes, so also we need a local controller, because it can happen that within these 15 minutes some things unexpected happens, especially with the electrical part that is varying very frequently. So we need a local controller to also adjust the set points that come from the central controller in real time. And a little bit more details about these functionalities. So the EMS makes use of 24-hour forecast of the weather, occupancy, and especially energy prices that vary hourly. And of course because it's model predictive control, so it needs models, simplified models of all the involved systems. So we have also developed all these simplified models, mainly RC models, that enable to project the behavior of the systems in the future, and also is fed by measurements from the sensors. And it uses all this to solve the optimization problem every 15 minutes and create an optimal planning of the resources. So, for example, in the case of the dual source system, to choose the most efficient source at every moment, because it knows the performance depending on the temperatures of these both sources, to anticipate the cheapest hour for charging the electrical battery. Of course, this maintaining the comfort at the desired boundaries. But the overall goal is to reduce the costs by shifting the thermal loads to the cheaper hours, because it's a cost-driven optimization so far. And by doing that, since we have also solar energy, it also optimizes the use of renewable energy sources, because since you have free available energy, then the optimization will tend to optimize its use. On the other hand, so the fault detection and diagnosis algorithm is aimed at detecting some common faults, such as evaporator fouling, compressor valve leakage, liquid line restriction, and refrigerant overcharge, for example. And we are trying to detect the degradation of the COP for this type of variable capacity heat pumps. And the goal is to detect efficiency drift of at least 10%, using sensors already available in the heat pump, so not adding any additional sensor. And then the algorithm creates alarms and diagnoses the fault. We have tested this in both in simulations and in laboratory experiments, so we can see the COP that we emulating the faults, the COP that drifts over time, and we're able to detect that. So just shortly some overview of some results that we have obtained. So with the energy management system, here you see the energy imports of reference control compared with the energy management system, and highlighting the periods of high prices. So with the energy management system, we concentrate the imports and the periods of cheap electricity, leading to cost savings of 11 to 47% in the case that we have studied, and increasing the seasonal COP thanks to this knowledge of the performance in different conditions. For the fault detection, we are able to detect this COP drop from 7%, which is quite satisfactory, and to diagnose every fault except for the evaporator fouling. And here you see some graphs showing the degradation of the COP in function of the intensity of the different faults that we have tested. So this is a bit an overview of the performance that this algorithm can bring further than just the systems in themselves, so how to optimally manage them. So thank you.